Okay guys, in this video we're going to continue our look at polynomial functions, but we're going to start our journey with just looking at a very simple type of polynomial function that we tend to classify with its own special name even. We refer to these as power functions. And so we're going to make a little note here that a power function is a type of polynomial where it is just a monomial. And so with respect to what these functions tend to look like, we say that they are functions of the form y equals, or we can say f of x equals, but a times x to the nth power. And so we get this one-term polynomial that has some leading coefficient here, a, and some exponent or degree, n, but that's all there really is to these polynomials. And so looking at these, I think a really good example of a power function would be something like y equals x squared and y equals x to the fourth. And so what I'd like to do is, let's do this. Let's kind of give an example of some power functions here. If we said f of x equals x squared, and we said let's let g of x equal x to the fourth, the very first two power functions that I want to look at are these two that happen to have even exponents. And so what you're going to see is, if we look at how these behave around the origin, we'll make x go here, we'll put f of x here, and we'll put g of x here. What I'll do is I'll put in -2, -1. Let's put in -1/2, even though I don't like to go by uneven scale increments here. We'll put in +1/2 as well. And then we'll put in +1, we'll put in +2. What I know is when we plug in these values and we square them, we always get positive outputs and we get the squares of our inputs. So what I get is -2 squared is 4, -1 squared is 1. -1/2 times -1/2 is positive, and if we're multiplying straight across, we actually get a number that's smaller than what we started with, 1/4. 0 squared then would be 0. A half squared would be a positive 1/4, and then 1 squared and 2 squared would be our 1 and our 4. And so when you're looking at this graph up here, you're going to notice that y equals x squared is this highlighted graph, and it says that it goes through 0, 0, 1, 1, -1, +1, and we got those points on here, but also some points we didn't put on, where like -1/2 went to a fourth, and +1/2 went to about a height of a fourth. 2 went to 4, so that's up here somewhere, and -2 went to also +4. When we look at now taking things like g of x and having it to the fourth power, these things get multiplied a lot more. So what would be the impact on our graph here? Well, -2 to the fourth power would be like -2 times itself 4 times. It'd be like 4 times 4, that'd be 16. Okay, and so we're going to get the same thing down here. We can see that this is definitely some even function. If we take -1 to the fourth power, we'd get a +1 here and here. If we took 0 to the fourth power, we would get 0 here. And if we took -1/2 to the fourth power, we would get -1/2 times itself 4 times, which actually comes out to be a +1/16. And so we're going to get that here as well. And so some things. First things first, I want you to notice the difference between x squared and x to the fourth. If you could point out some similarities, what I would point out is that 0, 0 is on either of those power functions, and also so is 1, 1, and -1. 1. And so in terms of looking at some similarities here, I think they have the same vertex value here, and they both go through 1, 1, and -1, comma 1. Now what I want you to notice is that once you get outside of this -1 to 1 range here, so to the right of 1 or to the left of -1, the x to the fourth tends to start growing a lot faster. And the reason why is because we're taking a number that's either bigger than 1 or less than -1 and taking it times itself 4 times. It's going to get rather large, whereas our squared graph only took it times itself twice outside of this -1 to 1 range. When we look at between -1 to 1, how do these graphs compare? Well, I noticed that between -1 and 1, so at -1/2 and +1/2, our squared function was at a height of a fourth, but our to the fourth power function was at an even lower height at 1/16, because now we're taking numbers between -1 and +1, which are proper fractions, and multiplying those by themselves a lot of times, which actually makes them incredibly small. So with respect to power functions, what do I know about their graphs? I know that they all kind of look similar if they're y equals x to the second, or x to the fourth, or x to the sixth, or x to the eighth, or x to the 10th. They're all going to go through 0, 0, -1, 1, and +1, 1. It's just the extent to which they are flat in between those values and blow up outside those values. So a power function, if I look over at Desmos here, you can see that I have x squared and x to the fourth already graphed. I would say, generally speaking, what I could do is I could turn on this ax to the n here, and looking at any graph where the n value is 2 or 4 or 6, you start to see that with these even graphs, they all look similar in shape. So there's to the 6th, there's to the 8th, there's to the 10th, you can see that they all go through 0, 0, negative 1, 1, and positive 1, 1. It's just that the higher the power, then the flatter they tend to be between this negative 1 and positive 1, and the faster they tend to grow outside of this negative 1 to positive 1 range. So next up, we have to kind of take a look at what would be true if I didn't have even exponents but odd exponents. These tend to all look like y equals x cubed. And so we're going to do another quick example here. If we had even power functions, we tend to get a table like this. If we look at, say, an odd example, and so this would be like maybe f of x equals x cubed would be a very basic power function. And we say, how about an odd one, x to the 5th here? So when we make a table this time, and I think it's worth noting that we'll use a lot of the same values here. We say f and g. We'll go negative 2, negative 1. We'll go negative 0.5 to lessen the confusion, 0, 0.5, 1, and 2. We know that when we plug all of these inputs into our cubing function, they just get cubed. So negative 2 cubed, negative 1 cubed. Negative a half times negative a half times negative a half would be negative 1 over 8. 0 cubed. Then here we get positive 1 over 8, positive 1 and positive 8. This is just a testament to the fact that these odd power functions are themselves odd functions. And so what would happen if I were to go through again and take things to the 5th power? Well, negative 2 to the 5th, that would be negative 32. So positive 2 to the 5th would be positive 32. Negative 1 to the 5th is negative 1, so positive 1 to the 5th is positive 1. 0 to the 5th is 0, and negative 1/2 to the 5th power is negative 1 over 32. It's not high off the ground at all, and this one's just the same. It's really hugging the axis there. So when you look at these graphs over here again, these all look like a cubic, but they go through 0, 0, 1, 1, and negative 1, negative 1. In between negative 1 and 1, the higher the power on your power function, like x to the 5th, you're going to see that it gets really, really flat between negative 1 and 1. But outside of 1 and negative 1, it starts to grow really, really fast, whereas our cubic function just kind of was this nice smooth curve in between here. And so again, if we go over and we play with Desmos here, I suppose if I start making my degree be odd, okay, and so we're going to go back and turn these two off here. But I want you to see that, I suppose, oh, where am I missing it? And turn these off here. That's better. If I make my degree, say, sorry, not my leading coefficient, my degree 3, we can see that we get this nice cubic function, 0, 0, 1, 1, negative 1, negative 1. But as I make this a 5, it looks the same. The difference is it didn't just go through 0, 0, 1, 1, negative 1, negative 1, but it was really flat between negative and positive 1 and grows faster once we get beyond x equals 1 or to the left of x equals negative 1. We make this a 7. Even flatter in the middle, grows even faster on the outsides. If I make this a 9, kind of the same story. So what's our intent here? Why do we want to know this? Well, because what I'd like to be able to do is sketch the graph of just some basic power functions. And so when we look at these two graphs here, you'll notice that there aren't a lot of terms to these polynomials. And in this first one here, what I notice is that it's just negative x to the 5th. So with respect to what I know this is going to look like just plain x to the 5th, but because of this negative in front, it's going to be reflected over the x-axis, okay? And so if I wanted to get a proper sketch of this here, we say if this is 1 and this is negative 1, I know that I would get a graph that looks like the x to the 5th graph, which is the same as x cubed in that it goes through 0, 0, 1, 1, and negative 1, 1, and would do this. But it should be reflected. So if this is what our cubic graph looks like, maybe I switch my colors to like, let's do an orange-ish. I'll try. It goes through 0, 0, but it's been reflected over the x-axis, and so it goes through 1, negative 1, and negative 1, comma, positive 1, since these 2 points flip over the axis. And when I draw this, because I know it's to the 5th power here, I'm just going to come in real steep and try to make this real flat in the middle. Flat, flat. Try to come in below here. And then just make this real steep again. And so you can see that this, if this is y equals x cubed, this y equals negative x to the 5th looked a lot like it. It was just reflected over the x-axis and really flat here in the middle, but growing really fast outside of negative 1 to 1. So how about letter B here? Well, I noticed that this is kind of like a power function, but it's the 4th power, so it's going to look like y equals x squared. Okay, and I also know that it has an h value here. It's been shifted left 1. So if I were to sketch this, I'd go left 1 and draw a dot. And because it's like our squaring function, I would go right 1 and up 1. And because of its symmetry, I'd go left 1 and up 1. But when we sketch this, we'll just come in real steep here on the outsides, make it flat in the middle here. Really, really, really flat. And then we'll leave real steep, since it's going to climb faster than our x to the 2nd graph on the outside of this little -2 to 0 range, but be really flat in between those.